Um, so depending on what material that we are dealing with, depending on the solution, the concentration, we would have different stability of electro electrostatically stabilized colloid. Okay, the total potential energy is the sum. Total energy is the sum of van der Waals attraction and the electrostatic repulsive energy. So total potential energy, we added up x distance and negative for attraction, positive for repulsion. Okay, and we would have different behaviors between the different types of suspension. One type, something behaves like this. When they are very, very far away, the energy is essentially zero. Makes sense, right? Everything when they are far away, the interaction energy is very, very small. And then when they get closer and closer, they would have what? Negative for attraction. They have pretty large van der Waals force compared with electrostatic repulsion. Okay, and of course you cannot get too close. So roughly at a certain distance, we are what? Reaching a kind of minimum total potential energy. Okay, so in this case, it's kind of we can say the repulsive force is weak, and the particle attract each other, and at a certain distance they reach kind of like equilibrium distance. They so-called agglomerate, but the agglomeration distance is slightly larger than 2r. Make sense? Because 2r is meaning what? A particle directly touching, but the in a solution there's always something in there, so they are not directly touching. Okay, slightly larger than that. Negative, which means particle attached to each other and they have a tendency to drop. On the other hand, we may have something different. When we have gradually increased the particle surface attached electrical charge, um, the repulsion would be stronger, but thermal activation can sometimes still knock the system into flocculation, something like this. Again, very far away, you have almost no interaction. And then when you get closer, because there are surface charge and you are getting into what? Positive means what? Repulsion. Because there are surface charge, the particles start to repel each other. But on the other hand, you probably do not have enough surface charge, which means by thermal activation, by atoms heating it randomly, we may knock the system overcome this barrier and knock the system into where? Into here. This is the system where it's kind of at a happy equilibrium. Make sense? Which means initially the system may be pretty stable, but you let it sit a while, the thermal vibration, the random heating cause the particles to overcome their what? Electrostatic repulsion, and it become unstable, become attached to each other, and now everything become happy and precipitate. Another behavior. For example, this could happen when the colloidal suspension, you add a little bit of electrolyte, but not enough. A little bit, not enough. Okay, and then another one would be, okay, the repulsion is large enough to form stable solution. The stable colloids. Far away, 0, and as we get closer and closer, getting positive, more and more positive, repel each other. Okay, and at a certain location, they become again a local minimum, which means they are at that distance, they are most stable. They're most stable. When you get closer, it's going to increase. When you get further away, it's also going to increase. When you get closer, it's going to increase because really the charge really starts to repel each other. When you get further away, it starts to increase. Why? Because remember, there's still some van der Waals force. There's still some van der Waals force. When you get further away, van der Waals force wants to what? Pull them together. So that's why somewhere you get a positive equilibrium here. And finally, we would have the system that is extreme case. There's really strong repulsion from each other, which is rare, and it happens when the repulsion is so large that only allows very low solid loading. Very low solid loading. Really, they want to repel each other. You cannot put a lot of high solid loading that make them stable. Okay.